This
Yeah.
conference will now be recorded.
So the first question is, what is kernel? So basically kernel which you see is nothing but a computer program. Yes, it's just a computer program, but it's running at the core of the operating system. Means just after the hardware layer, you have a kernel and that is running on the core level and generally has a complete control over everything in the system. Mind it, it has everything, all the control on your system. That's a kernel. So here you see bottom layer you have hardware, on top of your kernel, and then top of that we have a user level applications which you consume like browser and all, notepads and all kind of things. So next question is where kernel program runs. So kernel program runs in the memory. Okay, so it is a portion of the operating system code. It is a portion of operating system code that is always resident in the memory and facilitate interaction between hardware and software component. So this always runs in the memory. When kernel program runs, so when kernel is one of the first program loaded on startup. So when you switch on the laptop or desktop, then the first program which get loaded in that's a kernel. And after the bootloader means if you go to the BIOS, you can decide bootloader whether it's a CDs or disk or all this stuff. So likewise. So when kernel program runs. Now these are the types of kernel. There are a lot of types of kernel. We have microkernel, monolithic kernel, hybrid kernel, nano kernel, exokernel, and so on. So one of the kernel which we are using is monolithic kernel. Okay, the one we'll be using for all of work, monolithic. So what are the roles of kernel? So roles of kernels is doing a task management. Task management means I'll put it in this way. See, this is a task manager, and you see this all tasks which you see a lot of processes, CPU allocation, RAM allocation. Go to the detail view, you will see better. See here. Okay, and this one also. Yeah, this is the better. So these are the tasks is running on my laptop. You see, each of these has a PID status is running, and each of these process running with certain user. You see here, Rajesh Kumar, local user, system user, and consuming lots of CPU here. You see, these are the CPU. You notice that most of the processes which is running is not consuming the CPU. Have you noticed this ever? Only the here first 2 and 3 processes are consuming CPU, but RAM, if you see, almost every process is consuming. Correct now? All of you? Architecture
Yes.
x64. So yeah, this is that called task management. So that is taken care by kernel. Any communications you send to the operating system, that is also taken care by kernel. Memory management, I was just showing you the task manager which has a memory utilizations also. Which process should get how much memory and CPU and all. That is also taken care by kernel. Timer management, interrupt handling, event handling in the kernel, that is also taken by kernel. And device input output management, that is also taken by kernel. So device input output means keyboard, mouse, all this input output and all kind of things is there, is managed by kernel. So yeah, full kernel control all hardware resources, i.e. memory, cryptography via device driver, arbitrates conflicts between the processes concerning such as resources, and optimize the utilization of common resources, which includes CPU and cache uses, file system they managed by kernel, network socket managed by kernel, memory management by kernel, devices management, input output, and all stuff like that. Any idea who's this? Any idea who's this?
Maybe Linux
Linus
Torvalds.
Torvalds.
Yeah, Linus Torvalds. So he's the father of Linux actually. In fact, he's the father of Git also. I'll teach you Git, and he's the one person who developed the software, Linux kernel and Linus Torvalds. Okay, so Linux kernel, the one which you see, is the free and open source but monolithic modular multitasking Unix-like operating system. Okay, it was originally authored in 1991 by Linus Torvalds, and it was for the i386 base architecture and so on. So we understand that use of Linux kernel. Linux is deployed on a wide variety of computing such as embedded devices, mobile device. Do you know that Android phone, the one which you're using it has a Linux kernel itself? Did you know that? Hello?
No, Rajesh, I was not aware.
Yeah, so it is a Linux kernel only. Android operating system is using Linux kernel, minimal Linux kernel. Personal computers, servers, mainframes, supercomputers, and all. So now bootloader. So if you remember that bootloader, I talked about it. When you start the system, then bootloader boot the some of the storage and something get loaded in the memory. So what is a bootloader? So bootloader, also spelled as a bootloader or boot manager or bootstrap loader, is depends on, is a computer program that is responsible for booting a computer. So this is a kind of is embedded in the BIOS itself, your motherboard, and this will be helping you to boot the computer. Okay, so how bootloader works? So what happens when a computer is turned off, its software including operating system, application code, and data remain stored in the some non-volatile memory, just like a hard disk. But when your computer is powered on, when you start the computer, it typically does not have an operating system or its loader in a RAM. So what happens? The computer first execute a relatively small program stored in the ROM, read-only memory, and later EEPROM and NOR flash. Okay, along with some needed data to initialize the RAM, especially x86 system. To access the non-volatile devices, usually block devices like hard disk and all, or devices from which the operating system program and data can be loaded into RAM. So here, bootloader basically when you switch on the system, basically bootloader is a kind of program which get loaded in the ROM, and this software, what they do, they load your hard disk, and the hard disk has your kernel file system and other file system, and that operating system, kernel operating system, get loaded in the RAM. That is how it works. So see that here in a simple visualization, power on the ROM code which has a some bootloader booting devices which get loaded running, and bootloaders call the kernel which is there in the hard disk. Are you understanding, all of you? All of you?
Yes. So, Rajesh, this booting device is there, right? That will be there in RAM cache, ROM
Booting
cache.
device. Bootloader will be running in the ROM, but the
Hmm.
kernel will be running in the RAM. So bootloader will load those files in the RAM. So ROM is like a very minimal memories will be having built in your hardware, I mean motherboard, and that will load the some simple software. So BIOS, when
Okay.
you go for it, that has a bootloader. You can select what bootloader you want, some of you might have done it actually.
Yes, yes, I'm aware of that.
Yeah. So powered on, load bootloader in ROM and load kernel code in RAM. That is a something. So if they ask you, okay, when you start the system, what happens? So you can say when we start the system, bootloaders running in the ROM, and then bootloader is a kind of software which load the kernel, which is located in the hard disk in RAM, like that. Now this is a detailed architecture. Probably you don't need to go into that detail, so I'll just skip it. Now this image is very important, and I will drag this image a lot. Look at this here. Then here it is the workflow. Okay. So step number 1, step number 2, step number 3, 4, and 5. So first thing what happens? Bootloader running in the room. After that, first stage bootloader, which recall the memories, and second stage bootloader, which set up the some environment, and the fourth one, which basically loading the kernel. and then fifth one you load the root file system, which is located in the your disk. So now if you see that little bit carefully, the first, second and third is running in the bootloader. Okay, and then fourth one is running in the kernel space. So here bootloader space, kernel space, and then root file system which get loaded in a user space. Okay, so there are three spaces: bootloader space, kernel space, and user space. So in the bootloader space, all the bootloader related work happen. The program runs in the ROM, and then in the kernel space, kernel running in the RAM, and after that user space, you have all the file system, which is your file system which you have, right? Windows or Linux file system, root file system you call it, you have it. So it get loaded. So now the question is, okay,
Rajesh,
bootloader is
Rajesh, are we going to discuss the first stage and second stage and only deep afterwards, or this is
no,
like
not
overall?
needed. Huh,
Not
just a
yet.
overall. Huh.
Okay.
So your important thing will start with the kernel and user. Okay. So now the question is, what is a kernel space and user space? That is important. Okay. So here, user space and kernel space is you need to understand very wisely. So what happened? Computer OS usually segregate into the two space area. Here you see computer space, which is 4 and 5th, usually is getting is you know segregated in the two area. One is one is user space, one is kernel space. So I'll put it in this way: computer OS usually segregates virtual memory into user space and kernel space. Virtual memory means whatever the memory which you assign to operating system use it. They divide into two areas: virtual memory which includes user space virtual memory, kernel space. So here in user space you run some user based application, kernel space you run the kernel specification. So let's understand that. The kernel performs a task such as running processes, managing hardware devices such as hard disk, and handling interrupts in this protected area called user space. Remember that kernel is running inside in a virtual memory space called kernel space. Okay. Now all the application which you run that is running in the virtual space memory called user space. So in contrast, application programs such as browser, word processor, audio, video, players use in a separate area of memory called user space. So whatever the memory you assign, no virtual memory, divide into two part. One is kernel space and one is user space. And the in a kernel space virtual memory, all the kernels is related program is running, and in a user space virtual memory all the user related applications. So these are two virtual memory space. Are you understanding, all of you?
Yes.
Yes, yes.
Okay, so why there's a two segregation, why they divide the memory virtual memory into two part? So basically what is happening, I'll tell you in a simple way. See, you are the user who's running some software, and you may have some bad software. So bad software, if it is running in the same virtual memory area where the kernel is running, so you may disturb the kernel health actually. That means your programs may destabilize the operating system, because kernel, if it is not running, your operating system will shut down, correct? So what is happening? So user are forced to run in the user virtual machine virtual memory, and kernel is running in the kernel virtual memory, which is not accessible by anyone. So here, the primarily this separation serve the provide memory protection and hardware protection from what? Malicious and irritant software behavior by the user. That means you do not, if your program should not create a instability in the kernel. Okay, so this separation prevent user data and kernel data from interfering each other and causing instability and slowness, as well as preventing malfunctioning application from affecting other application or crashing the entire operating system. So basically, kernels should be stable, should be running no matter what kind of application you are running. Okay, it should be stable. So virtual memory divided into two part: kernel space and user space, just for making the system stable. Okay, so look at this here. So virtual memory, Divided into two part. Kernel space, kernel runs in a supervisor mode and has access to the user. Mind it, kernel runs in a supervisor mode and has access to the user section as well. That means the kernel has a complete control of the user space. Okay, but user space has no control on kernel space. Okay, so you see that kernel space running with a supervisor, and supervisor has access to user space and kernel. That means kernel space, any programs can do anything with the user space, but user space has a no control on the kernel space programs. Okay, so this virtual memory divided into two part: user space, kernel space. Kernel space is running in the supervisor mode. So now the question is, okay, so the question is, when you run applications in user space or virtual memory, then how these applications request the system for the resources. Resources means CPU, RAM, disk and all. Because user space has no access to your RAM, user space has no access to CPU, user space has no access to the disk and input and output, nothing, no access. So how this has happened? So this is a very important one. So all the programs which is running in the user space is making a call to the kernel space, and that is through system call. We call it system call. What we call it?
System call.
Remember that one of my interview, I failed these questions maybe 10, 12 years before. I still remember that moment. They asked me, hey, we are running the application in the user space and kernel space. How this application running in the user space is calling, how the application running in the user area is getting the RAM allocations and disk allocations and CPU. I said like just make a call through kernel, but that was not right answer. You should tell it is making a system call. That is the name of the program itself, system call. So using the system call, you request a kernel, hey kernel, I want this much of RAM, I want this disk, I want this much of CPU, I want this much of permissions. Are you understanding, all of you?
Yes.
Yes,
Yeah.
yes.
So now system call is a basically one program which has a multiple methods. It's like a program. Everything is program, right? So multiple methods. Some of the method is get pid. So get pid is a method. Let's say you're running bash. Okay, bash you're running in Linux. So bash to run, you need to have a PID. Say, let me show you that here. Look at the PID. So PID attached to the memory and CPU allocation and users also. So you want to run bash. So for that you need a PID. So which method will get the PID? Get PID. You want to open any file. So which method in the system call will run? Open method. So likewise, we have a lots of method. You don't need to remember that, but you should tell, hey, system call is a kind of interface between the application running in user space and kernel space, and system call has a multiple method like a get paid, open, and all these things, get user, get MNT, all these things you have it. No need to remember all these things, but you can tell. Okay, so here you see bash is application, and they get the all the resources from the application running in the kernel space. So kernel space, you have all the library, pid, net, block, xfs, and all many things. Okay, so look at this here. Here you have a hardware. On that you have a kernel space which is running your kernel, and then on top of that user space which is running your application code. Okay, so yeah, user space and kernel space, this is how you can take it as a summary. So very good image I got on the Twitter. The Linux kernel has millions of lines of code. Read and write files, that's a function. Decide which programs get to use what CPU, how much CPU. Make a keyword work and all kind of things. So that all these things done by Linux kernel. When Linux kernel code runs, that's called kernel space. When Linux kernel runs, that's called kernel space in the virtual memory. And when your program runs, that's in user space. Okay, so here after this, there's a something called context switching. What is the context switching? So see that here, your program time to write file. So that's my job. Which job? Kernel job. So anything you inform, everything is done by kernel actually. So you say you want to open a file, you want to write a file, you want to run some commands, you want to do something. So that will be done by kernel. So kernel is running in the kernel space. What will happen? So kernel, your program which you're running, when you move to the kernel namespace switching, then it's called context switching. Time for a context switching to the kernel space. Let me show you. Look at my screen. Look at this. I don't know whether it's visual or not.
But you said the user space does not have access to kernel space, right?
Yes, yes, no, they do not have. I want to show you. I want you to focus on this part. See, this all allocation is 0. Only first 3 things is getting CPU. So sometimes CPU is getting to go to meeting, sometimes system, sometimes snipping tool or something like that. Look at this. So what is happening? CPU, see, RAM is consumed by everything. Okay, RAM is consumed, sorry, here, RAM is consumed by here. Okay, so here context switching from here CPU, then again CPU, again CPU, again. So this is called context switching. Okay, we'll discuss in little detail and all. So that is context switching. So here you understand your program switches back and forth. Okay, so that is called switch to kernel space for running a program, getting resources, and we are back to the user space after getting the resources. Output, you will see that. Okay, so like this. So yes, you see that here again, same image in a different visualization. You have a hardware and then kernel space and then user space. These are the detailed one. This is the all the functions which you have, which is being called. So you don't need to remember this one, just for knowledge purpose. Okay, so now let's discuss about the Linux architecture. So Linux architecture, at its core, you have a hardware on top of your kernel, and top of all your user programs, you have a shell, and on top of that, all your user programs. So shell is basically bash shell, corn shell, C shell, and all, which helps you to interact with the kernel basically. Okay, so shell is running and all the user programs is running in the user space. Okay, so look at this image here. A hardware running the kernel, and kernel you have a system call interface. Mind it again, same thing. And system call, user, all the applications talk to system call to getting the resources, and kernel allocate the resources and get it done. Okay, so same image, system call. So here you see user program have talk to user interface talk to the system call will talk to the kernel and get the all the availability of it, and then on top of hardware. Okay, so in a computing, a system call, commonly abbreviated to a syscall, is a programmatic way in which a computer program requests a service from the operating system on which it is executed. This may include hardware related services or hard disk or any new processes you want to create, or communication with the integral kernel services such as process scheduling. So system call provide an essential interface between a process and operating system. Remember that. So in the most system calls run only be made from user space processes. Okay, for security reason. Okay, so by now you understood that what is a system call. All of you, any questions? All
Yeah,
of you.
you already mentioned it, right? Like the user program will request the resource, example CPU or memory, to the from the kernel space.
Using syscall, system call. Yeah. Yeah. Now guys, if you want to deep dive little bit more into the system call, you don't need it though, but again, just for the high level, system call provide the service of the operating system to user program via the API, application program interface. We call it API. So this provides an interface between the process and operating system to allow user level process to request services of the operating system. So syscall are the only entry point into the kernel system. That means if you want to talk to kernel for any resources, syscall is the only entry point. So services provided by system call, which includes creating of the process and management, main memory management, accessing the files, directory and file system, device handling, protection and networking. That means in a simple way, I tell you, if you want to run any software, any application in user space, you need a PID, process creation and management. So that is done by system call. If you want to allocate some memories to the process, that is done by system call. If you want to access any files which is stored in the hardware, that you want to write a files, that is done by system call. If you want to access any system input and output and communications, that is also managed by system call. If you want to protect the system and kernel, that is also syscall. And you want to create a network, modify the network, that is also called by system call. So users process is making all this call through the syscall, which is API, to the kernel, and that is how it works. This is a detailing image, it's not required to discuss. So yes, type of system call: process control, file management, device management, information maintenance, and communication. So how to system call works? So here there's a two things which I said: API. So here, how to system call works. The Linux kernel provides several interfaces to user space application that are used for different purposes and that have a different properties by design. So there are two types of application programming interface, which is called API in the kernel, Linux kernel, that are not to be confused. So that is the Linux user space API and the kernel internal APIs. Okay, so these are the two APIs you have where you can interact with these APIs to talk to the kernel space. Okay, so the Linux API is the kernel user space API, which allow program in user space to access system resources and services of the Linux kernel. Okay, so Linux API is the composed out of the system call interface of the Linux kernel by GNU, C library by GNU, and libc groups, libdrm, libalice, and libbevdev, and so on. So you don't need to remember all this thing. Just understand that system call has a few interfaces which is making the things accessible from the user space to kernel space. There's another interface which we have, ABI. The term Linux ABI refers to the kernel user space API. The application binary interface refers to the compiled binaries in the machine code, and any such ABI is therefore bound to the instruction set. Okay, so there's a differences between the API versus ABI. This probably we don't need to get into that.
Can you tell about that last previous slide, the internal API? Could you
Yeah.
repeat? Sorry.
Yeah, so here internal API, that means that is running in the kernel internals. So there are several kernel internal APIs utilized between the different subsystem. So basically there's a kind of program which is running, making it available, and user space talk to API. API send this request to the kernel space and kernel space respond it. So this is through API and APIs. Got it?
Yes. Okay. Thank you.
Okay, so this is also interface in a deep dive thing, so you don't need to understand this one. It's more complicated. And so, yeah, so these are the list of method which is made by system calls. Some of two of these I showed you in the previous slides, but here you have a fork, exit, wait, open, read, write, close. Some of the others one also you have it. So you can check it out. I'm just ignoring it because this method you don't need to discuss. Yeah. Now, I'm just ignoring it, many things. Okay. Now, this is something which is very important for all of you. Process and threads. Okay. So what is a process? Let me show you here. So here you have a process. This is the process ID. Okay. Okay. And right now I don't have a Linux box. Oh, yeah, I have a Linux box. Let me get WSL, Ubuntu. This is Ubuntu running in my laptop itself. I'll teach you all this thing, how to set up your own environment in laptop. So this is running in the laptop itself. So here ps-ef, you see here, this is the PID and this is the PPID, you see. So this is the each processes which is running right now, you have a PID. Now I must remind you, this generating a PID is done from which module? So let me show you. I showed you that one. Here, see, create process. See, in this there is one method in a syscall. You have a method called create process. So this will in Windows and Linux, what we have, fork. Okay, so in Windows kernel we have a create process, and in Linux we have a fork. This create a process ID. Got it, all of you? Hello?
Application user does the system call, right? The user interface, the fork.
Any applications which you run, you'll make a system call. System call through some API. Which method will be executed in the system call? Fork method in
Fork.
Unix and Linux. Yeah. If you're opening a file, then open method. If you are reading a file, read method. Writing a file, write method. These all methods, these are the code actually, okay? We call it system call. Make sense? It's library. Okay, so now let's understand this way, thread and process. So here you see there's one process and you have multiple thread. Okay, so here you also see CPU allocated to the process. Okay, mind it, CPU allocation is to process, and whatever the CPU allocated to the process, it's shared by multiple thread. Okay, so one process, multiple thread. So now the question is, what is a process? So process is a computer program under execution, under running. Okay, remember, process is a computer program under running. So if you want to see in the Windows, there's lots of process. You see left side, these all are process. Okay, all are running. That's the reason you are seeing that here. These are the under running. Okay, so in Linux also, if you want to see, this is the process. Look at this here. These are the source running in my system. So process is an execution program under running. Now Linux is running many processes at any given time. Okay, we can monitor them on the terminal using ps command. I just now showed you, or on the system monitor UI. Linux processes are isolated. Please understand that Linux processes are isolated and do not interrupt each other executions. Okay, so one process is different from other process is different from other process, likewise. So with a PID, so how can you identify which process you are talking about? So each process will have a PID. Look at this PID. This process has this PID, this PID, this PID, this PID, and all. So each processes which you run, you get a PID, process ID. That is how you identify the processes. So since many processes are running at a given time in Linux, they have to share the CPU. So here you see, I'm putting in a way so many processes running. Now you have to share the CPU, right? So because memory allocations here is memory allocations is given to every processor which is running, but CPU allocations is not given to every. So now they have to share the CPU, correct? So since the many processes are running at any given time in Linux, they have to share a CPU. The process of switching between two executing processes on the CPU, it's called process context switching. I don't know whether it's visible or not. Can you see the process context switching in my laptop? Look at this here. Just only focus on the my cursor. See 95 to 1. See that switching? So sometime you get this process to this process. Are you able to see that? I don't know whether it's visible or not. CPU, look at the CPU, first 2-3 processes. So here CPU allocations is at one at a time. Okay, understand that. For running any process, understand this. For running any process, you need a memory. But for accessing any application and process, you need a CPU at that time. And CPU, see, one at a time they are allocating. So they're switching between this, and this is happening so fast, you'll not be able to measure in the microsecond and second or something, millisecond. It's in nano and minicular actually, very fast. But you are not able to see that fast because it's like this. So that is called that process is called process context switching. So process context switching is very expensive. Why? Because one process, when the CPU is switching from the one process to another process, it takes few seconds. What happens? Whatever you did in the previous process, it first stored, and then after storing, let's say you are browsing google.com. Okay, so that's the one process. So what happened before switching the process? This your system store that you are browsing the google.com. Okay, so next time you will be on the google.com itself. Okay, so what happens? Process context switching is expensive because the kernel has to save old registers and load current register, memory maps and other resources also. So this is very expensive. So what we do in order to avoid this, that is where that we introduce the process called thread. Okay, so what is a thread? So thread basically is a lightweight process, but there is a thing is a process can do more than one unit of work concurrently. That means if you have a one process and you have multiple thread, the thread this process can do more than one unit of work concurrently by creating one or more threads. These threads, being lightweight, can be spawned quickly. So let's see an example and identify the process and its thread in Linux. So how can you do that? ELF command you run and you will get to know how you can find the thread. So ps-ef, ELF also you can do that. ELF. See here. So here you can check that which PID have a multiple thread. So right now I don't see here this mid one and number of thread. No, not able to have in this scenario. You don't have it. Let me show the image of it. So here PID, LWP and NLWP. NLWP is the one here you see here. This is not coming. Okay, because of this is a WSL. Yeah. So here you don't have a threading. Okay, but I'll show the image in the PPTs. Okay, so you'll be having three if you're running the virtual machines or physical PID, LWP, and NLWP. So you see here like this: PID, PPID, LWP, NLWP. So NLWP will tell you the how many threads you have. Okay, so you just let me run this command, change this ELF. So here L is capital and F. Let me see if I get it. NWP. It. So see here, not here. This you see. So this is the process ID 1, and they have a 14 thread here. Okay, there's the PID 1 and 14 thread. That means whatever is running in this process, you have 14 thread. That's a small process. Okay, so likewise you can see the thread. So why we use threads? So we can easily identify single threaded or multi-threaded processes by using their NLWP values. So PIDs, which is like a 690 here in this image, 690 have a 2 and 701 have a 2 and 4 respectively. Hence they are multi-threaded. So with the 2 and 4 threads, all other processes have their 1 NL means number of threads 1 and are a single threaded. On careful observation, we can see the single thread processes have the same PID and LWP values as they are on the same thing. However, in a multi-threaded process, only one LWP matches its PID and the other have a different values of LWP. And also note that the values once assigned to LWP is never given to another process. That means it's always unique. So here you see that this processes PID is always unique. You see here, it's not duplicated. Let me see. Look at this. This is always unique. Okay. So here, this is the thread. So single thread process, any thread created within the process share the same memory and resources of the resources. That is important. Why we create a thread? So a single thread process, any thread created within a process share the same memory and resources of the process. So that way the context switching when it happens is cheaper. So faster it happens, the computer is faster. In a single threaded process, a process and threads are the same as there only one thing happening. In a multi-threaded process, what happens? I just read the first paragraph only. In a multi-threaded process, the process has more than one thread. Such a process accomplishes multiple tasks simultaneously or almost at the same time. As we know, the threads share the same address space of the process. Okay, so that may what happens. So when you have a multi-threaded process, whatever the CPU got it to the process is shared by all the multi-thread, and all the threads can run simultaneously. So basically because of this, your machine, your output is faster. Okay, so therefore spawning a new thread within a process become a cheap, and this process is called context switching. Remember that this process called context switching. So see here, this is a single threaded process. You have multi-threaded process, and when in a multi-threaded process, each thread is sharing that resources whatever they have it. Okay, so thread internals I discuss. Yeah, so this is an interview slides. You need it to understand that. So what is the difference between process and thread? So process is a heavyweight process. I mean, heavyweight process applications. A thread is a lightweight process, also called LWP. Process has its own memory. Thread has no its own memory. They share the memory which is assigned to process. So thread share the memory with the parent process, another thread within the process. Now here in process, inter-process communication is slower due to isolated memory. That means one process switch to another process, other process switch to another. So this is called context switching. This is and this makes the system slow. But when you have a thread, inter-threaded communication is faster due to shared memory. In the process, context switching between the processes is expensive due to saving old and loading new processes memory and stack info. In the thread, context switching between the threads is less expensive due to the shared memory. So that is a major difference between the processes and thread. So now how you define you want to run application in the process or thread? It's all the design you make it, and threading programming languages people practices and make it happen. Okay, so these are more differences between the process and threads and so on. Okay, now scheduling and preemptions. What is scheduling? So scheduling, remember that's one of the work function of the kernel. So Linux kernel control the way that tasks or processes are managed on the system. So who's managing, who's scheduling, who's controlling all the tasks to the Linux kernel? So there is one component which is called task scheduler. Okay, sometimes also call it a process scheduler. Okay, so this component of your kernel is the part of kernel that decide which task to run next. So here, mind it, here you see that is deciding, see, look at little carefully, CPU. So now which task to run, whether it's a go-to meeting or system or DMW or task manager or audio or see, are you able to visualize this here? All of you? All of you? Hello?
Yes, Rajesh.
Yeah. So this, who's deciding which one to run first? Not you will decide. Who's deciding? So this is decided by scheduler in kernel. You can call it a task scheduler or process scheduler. Okay. So this makes it a core component of any multitasking operating system. Yeah. So this is more about the scheduler. Preemption. So what is the preemption? So there is one concept which is called in kernel, we have a preemption. So the theory behind the task scheduling is very simple. If there are runnable process in a system, at least one process must always be running. Remember, this statement is very important. if your system is running, that means at least one process is always running. Okay, so here your system is running. Let me tell you here in this, your system is running because of this one, PID1, sorry, this one, 4, PID4. This is the first process which should be always running. And if this is not running, your system will shut down. And that is the system anti-kernel file system is running. So if you kill this process, somehow your system will shut down. And this is all running in the kernel space. So here, that is important. I'll put it in this way. Your physical server is running because of the first process, PID1. Let me show you the first process in Linux also. My system, my Linux VM is running. here. Look at this here. My VM is running because of this first process. After 0, first process. So I'll put it in this way. Your system is running because of the PID1 physical server. Your virtual server is running because of the PID1. Your container is running because of the PID1. Remember this concept. Okay. So here preemptions. The theory behind the task scheduling is very simple. If there are runnable process in a system, at least one process must be always running. If there are more runnable process than processor in the system, not all processes can be running all the time. That means, therefore, some process need to be stopped temporarily or suspended. Okay, it's not like I'm saying stopped and delete. Stop temporarily and suspended so that others can be running again. So the scheduler decide what process in a queue will run next. That is the job of scheduler. As already mentioned, Linux, like all other Unix variant, is a multitasking operating system. That means that several tasks can be running at the same time. So Linux provide a the feature called preemptive multitasking, where the scheduler decide when a process is suspended. So I don't know whether you can see it or not, but if you see that many processes will be in a suspending mode. Uh, See, suddenly it got suspended. Look at this here, suspended. See here, suspended here. Okay, so this will be keep on happening by the operating system, so you don't need to worry about it, but yeah, this knowledge is important. So here, as already mentioned, Linux, all other or Unix variant, is a multitasking operating system. That means the several tasks can be running at the same time. Linux provide a so-called feature called primitive multitasking, where the scheduler decide when the process is suspended, and this the fourth suspensions is called preemptions. All Unix flavor has been providing primitive multitasking since the beginning. So this is important. Now next theory is concurrency of the kernel. So what is the concurrency in the kernel? So concurrency in the kernel is like concurrency is the executions of multiple instruction sequences at the same time. So that means you are executing multiple instruction sequence at the same time. So concurrent job has to run by the kernel. This concept is called concurrency. It happens in the operating system when there are several processes threads are running in a parallel. The running process. So let me show you the several threads. See, I'm running the Chrome, right, and Firefox. So let me show you. If you see that, where is a Chrome? See here, Firefox. So these are all the threads actually. Okay, so this is all concurrently running actually. So likewise. Okay, so concurrency is the execution of the multiple instruction sequences at the same time. It happens in the operating system when there are several process threads running in the parallel. The running process thread always communicate with each other through the shared memory and message passing. So that is called concurrency.
Rajesh, the PID of the Firefox was different, right? It should have the same PID, right?
So here, uh, right now in this, I did not get the you know PID, I mean PPID. Here you are right, all the PIDs are different. But what I'm trying to say, if you have a same PID and multiple threads are running, those this all processes can be concurrent. It will be running. Got it?
But isn't the PID should be same like for one process?
It should be same. It should be same. Oh, you're saying like Firefox to the PID because I run multiple Firefox instance, multiple
Oh, okay,
applications.
okay,
So
okay,
likewise, if I'm running, let's say one Firefox and then asking that Firefox to do multiple things, that is called concurrency.
okay.
And so on. So sync is don't need to do that. So yeah. So guys, this is all about Linux kernel. So let me tell you here, out of, let's say, if you are being asked 10 questions in the interview, out of which 2 questions to 3 questions will be from the Linux kernel side in any serious interview on the DevOps. So I would suggest you, again, you go through this discussion, and once you start working on it, you will get more comfortable and get going. Any questions so far, all of you?